Our focus is on getting started with Docker containers. We will look at the concepts of a container and how it differs from a virtual machine. We will examine container images in detail, along with the Azure Container Registry and the Docker Registry. Finally, we will explore containers in Azure. So what is a container? Well, a container holds everything required to execute the application. This includes the code, the runtime, the system tools, any required libraries, and the necessary settings for the application to execute as expected. Containers are lightweight software components that bundle the application, any dependencies, and its configuration into a single image. The image executes in an isolated user environment on a traditional operating system. This applies on a traditional server or in a virtualized environment. So, to summarize, a container holds everything required to execute the application: code, runtime, system tools, any required libraries, and any settings for the application to execute as we anticipate. And since multiple containers are executed by a single operating system kernel, this means that containers are more lightweight than virtual machines. So why are containers a hot topic at the moment? IT departments are under a lot of pressure to work at the speed of the business. They're required to increase agility, but also work under difficult environments. One area of pressure is the deployment of enhanced or new application code. Typically, deployments are required more frequently, and this problem is challenging to meet. Containers mean that every environment can look the same, and this simplifies deployment and also supports our maintenance. Containers are designed to help meet these challenges faced by IT departments. Containerization has a range of benefits. They work on the principle of rights: once run, run anywhere. Containers achieve portability between different clouds and different platforms. This means that they achieve velocity at a higher rate. Containers are extremely efficient. They use fewer resources than virtual machines, and they can deliver an optimized utilization of compute resources. Containers help IT departments to become more agile. They run anywhere, and they are easy to integrate with the existing DevOps environments. They also help to deliver higher speed and the delivery of enhancements to applications. This helps meet business requirements more easily. For example, developers can deploy monolithic applications as containers using microservices. This allows development teams to create functionality that meets the cadence they require to run at. It also helps them to operate within their own scaling policies. Containers offer improved security because they isolate applications from the host system. Note that containers are also isolated from each other. Containers offer faster rate of startup, and they are easier to scale. This is because they utilize fewer resources. They can be deployed in virtual infrastructures as well. Even in a native way, containers can be deployed onto bare metal servers. Finally, they offer easier management. The install, upgrade, and rollback processes are built into the Kubernetes platform. To summarize, containers can run anywhere. They can run on Linux, Windows, in the cloud, and they can also run with drones, Raspberry Pi, and IoT. Containers run on isolated user environments on a traditional operating system. This can mean a traditional server or a virtualized environment. You can even see some examples here that they can even run on drones, Raspberry Pi, and IoT projects. Containers provide a way to isolate applications, and they provide a virtual platform for applications to run on. Note that there are two main differences between a container and a hypervisor system. The container system requires an underlying operating system that provides the basic services to all the containerized applications. A hypervisor, on the other hand, executes virtual machines that have their own operating system using hardware virtual machine support. Together, this means that container systems have a lower overhead than virtual machines. Typically, container systems target environments where thousands of containers are in play. Container systems provide a degree of service isolation between containers. To summarize, a container is an isolated lightweight silo. It runs an application on the host operating system. However, they are very lightweight. They build on top of the host's operating system kernel. And containers contain only apps and some lightweight operating system APIs. They also run services that run in user mode. In contrast, virtual machines run a complete operating system, including its own kernel. There's also some differences in terms of the degrees of isolation offered by both technologies. Containers offer lightweight isolation from the host and other containers. This means it doesn't provide as strong a security boundary as a virtual machine. On the other hand, virtual machines provide complete isolation from the host operating system and other virtual machines. This is useful when a strong security boundary is required. The virtual machine operates a complete operating system, including the kernel. Therefore, this means it requires more system resources, such as CPU, memory, and storage. On the other hand, containers run the user mode portion of an operating system. This means they can be customized to contain just the required services for your application. This results in fewer system approaches. On the other hand, containers run the user mode portion of an operating system. Containers can be customized to contain just the needed services for your app, thereby using fewer system resources. Containers deploy individual containers by using Docker via command. When we deploy multiple containers, we can use an orchestrator, such as the Azure Kubernetes Service. For virtual machines, we can deploy individual VMs by using Windows Admin Center or Hyper-V. We can deploy multiple VMs using PowerShell or System Center Virtual Machine Manager. For persistent storage, we can use a virtual hard disk for local storage for a single virtual machine. Containers can use Azure disks for local storage. Alternatively, they could use Azure files for storage shared by multiple nodes or servers. In terms of fault tolerance, virtual machines can fail over to another server in the cluster. On the other hand, in containers, if a cluster node fails, any containers running on it are rapidly created by the orchestrator on another cluster node. To summarize, there are a few interesting differences between containers and virtual machines. To summarize, A virtual machine runs a full-blown guest operating system with virtual access to host resources through a hypervisor. In general, virtual machines provide an environment with more resources required. This means that applications are assigned and available, and they can use resources on the virtual machine. However, there may be plenty of resources being available on the virtual machine, which are not required by any of the applications. This seems quite wasteful. By contrast, a container runs natively in Linux. It shares the kernel of the host machine with other containers. It executes a discrete process, taking no more memory than any other executable. Therefore, it's very lightweight. Virtual machines include the application, the required libraries or binaries, and a full guest operating system. Containers, on the other hand, includes the application and all of its dependencies. They share the operating system kernel with other containers. This means they can run as isolated processes in user space on the host operating system. One exception to this is Hyper-V containers, where each container runs inside a special virtual machine per container. We can see here in this diagram where the dependencies lie for the virtual machines and the containers. A container image is a lightweight, standalone, executable package of software. It includes everything needed to run an application: code, runtime, system libraries, system tools, and settings. Container images become containers at runtime, for example, in Docker containers. Images become containers when they run on Docker Engine. Available for both Linux and Windows-based applications, containerized software will always run the same, regardless of the infrastructure. Containers isolate software from its environment. Containers ensure that it works uniformly, despite differences, for instance, in development and staging. So, how are containers launched? A container image is a lightweight, standalone, executable package of software. They can be images become. So what is Docker? Docker is an open source project for automating the deployment of applications as portable, self-sufficient containers. These containers can run on the cloud or on premises. Docker is also a company that promotes and evolves this technology. They work in collaboration with Microsoft and other vendors, and they operate with cloud, Linux, and Windows vendors. Docker container technology was launched in 2013 as an open source Docker engine. It leveraged existing computing concepts around containers, and it specifically came from the Linux world, using primitives known as C groups and namespaces. A C group is a control group. It provides a mechanism for aggregating and partitioning sets of tasks. That includes all of the future children of those tasks. They are arranged in hierarchical groups with specialized behavior. A namespace wraps a global system resource in an abstraction. This means that it makes it appear to the processes within the namespace that they have their own isolated instance of the global resource. In short, C groups specify the limits on how much you can use. Namespaces limits what you can see and therefore use. Specifically, Docker and Microsoft have a joint engineering relationship. This means they can deliver a consistent Docker experience for developers and operators. Note that all Windows Server 2016 and later versions come with Docker Engine Enterprise Edition. Additionally, developers can leverage Docker natively with the Windows 10 via the Docker desktop. Docker Windows containers work the same way as it does on Linux. It's the same Docker command line interface, API, image format, and content distribution services. So let's go through some Docker concepts. Docker is available in a number of tiers: Community and Enterprise. Docker overall is a platform for developers, and it's aimed at developers and sysadmins to develop, deploy, and run applications with containers. The Community Edition of Docker is closed source, but completely free. Alternatively, the Enterprise Edition is also closed source, and it needs to be licensed on a yearly basis. Docker Enterprise is designed for enterprise development and IT teams who build, ship, and run business-critical applications in production at scale. The Docker engine is designed with the enterprise in mind for enterprise development of a container runtime with security. It also is designed to meet an enterprise-grade SLA. Note that Docker is the vessel by which container images are packaged up and delivered. This is an automated process which produces images, which are effectively templates, which may then be run anywhere, on premises, in the cloud, or even on a personal machine, and they are run anywhere as a container. You can see here that Azure offers containers. It's one of the aspects where you can use containers in your environments. You can also have them available to you in the customer data center, and service providers may also offer them. This means that Dockerized applications can run anywhere. So there are many benefits to using containers, and some of these are identified here.